with the lecture. Like I said, this is our second to last lecture. Um, Today we're going to look at the exponential function, e to the x, and then on Monday we're going to do the same thing with sine and cosine. Okay. So our big goal today is to show that the function that we all know of as e to the x actually exists. And the question is, where do we start? Okay, and why are we doing this? So the reason we're doing this is just, we all know it exists, but we haven't all seen a definition of it, and we haven't seen a proof that it actually does all the nice things that we think it does. Okay, so it's important to actually see how we're going to define it, and then see how we're going to prove that it has all the nice properties that we know it has. Okay. But then the question is, where do we start with e to the x? How should we define it? I will open that up for answers.
Well, there, there's that nice limit definition of E, and we could put an X into that definition and define as a limit, perhaps.
Yeah, that's a good point. I guess that's kind of what we're gonna do. Um, what I'm trying to ask more is, okay, we can take it to be that limit, and we could say here's a function. It would be nicer if we defined it by like a property that it has.
Function that is underivative.
Yes. So that is what we're going to do in the end. We're going to define it as a function that is its own derivative. So we want the derivative of e to the x to be itself. And that doesn't quite do it. If you think back to differential equations, you have to do one more thing.
Constant term is 0.
Yep. Have to give it an initial condition. Okay. So today, we want to take that definition of e to the x, show that that defines a unique function, and then show that that function has all the properties that we want out of it. Okay? That's our goal. And then, it'll follow that there's a function, that it has an inverse, and we'll just call that natural log, and so on. Okay, so that's where we are. So our first theorem is going to say there exists a function that does this. We're not going to call it e to the x because we don't want to presuppose that it is our function until we know that it is our function. So here's our theorem. There exists a function E, we'll call it capital E. It maps from R to R such that, well, it does the two properties we want. Its derivative is itself. And at 0, it's 1. Okay, those are the two things we want to get initially.
Excuse me, should we say that this function is unique?
We'll prove uniqueness later.
Got it, okay.
Although actually I think this is the only theorem that we will prove today. Your book proves uniqueness later, and we'll talk about that. Okay? Okay. So what we're going to do to prove this is we're going to define a sequence of functions that get closer and closer to our goal. Okay? Now, if we were coming at this from the perspective of Taylor series, we would basically be defining the Taylor polynomials of e to the x. But we're not coming from that perspective. So we're going to almost redevelop those. So we're going to inductively define a sequence of functions e sub n by e sub 1 will be 1 plus x, and then for larger values, e sub n plus 1 will be 1 plus the integral from 0 to x of the previous one. And you'll note that obviously we changed the variable inside the integral as normal. You might worry about negative x because we haven't. Well, for negative x, we're just going to use the convention that if x is negative, then this integral is the negative of the reverse. Is that okay? Okay, and now in this theorem, I'm going to reference a lot of, in this proof, I'm going to reference a lot of theorems that we've proved. Let's start with the first one. So we're going to give an inductive proof that this is actually a good definition. Okay. So the problem is, in our definition of e sub n plus 1, we've got an integral. How do we know that integral exists? Well, we need to know that e sub n is integrable. Okay? Well, e sub 1 is continuous, so that means e sub 2 is well defined. Okay? You need continuity of e sub n to get that e sub n plus 1 is well defined, that integral exists. But then we have a theorem that says that if you are the integral of an integrable function, then you are continuous. Okay, and so this just gives us an inductive proof. So assuming that e sub n is continuous, then e sub n plus 1 is well defined. That's using the theorem that continuous functions are integrable. And then I actually looked at the reference. It's 7.3.4 says that it's continuous. Okay, and then you can see how this works inductively. That means e sub 2, n plus 2 is well defined, and then the theorem says it's continuous, etc., etc. And for our base case of our induction, it's obvious that e sub 1 is continuous because it's 1 plus x. Okay, so. Okay. You know, there's another approach to this. You know, you could just evaluate these things, and you could say, well, they're all polynomials, right? And we know that polynomials are continuous. and they have integrals. Okay, so we wouldn't need to actually use these theorems. Okay, so by induction, they're all well defined. Now we're going to use the fundamental theorem of calculus. This is the second part. E sub n plus 1 is differentiable for all x and its derivative is e sub n. Okay, so remember part 2 of the fundamental theorem of calculus just says that we can differentiate that that indefinite integral and we get back e sub n. Okay, now that's a good property to have. We'll use that in a second. Now let's just go compute these things. Like I said, they're going to be the Taylor polynomials. So by induction, we compute exactly what these are. Okay, you just think when you go to integrate 1 plus x, here, let me throw the definition. When you go to compute e sub 2, you get 1 plus the integral of 1 plus t. That would be t plus t squared over 2. And then you go to compute e sub 3, and you get 1 plus the integral of 1 plus t squared over 2, which would be 1 plus x squared over 2 plus x cubed over 3 factorial. And you just keep doing this. And when you get up to e sub n, you will have an x to the n over n factorial. Okay, so I'm just claiming that by induction you can see this. So you would, the inductive proof, you would say, well, it's true by definition for e sub 1. And then if you assume that formula holds for e sub n, you get the formula for e sub n plus 1. Okay? Good. Now, we wanted to define the exponential function to be the limit of these guys, so we need this sequence of functions to converge. And what we would really like is for this derivative property to come over to the limit. And to get the derivative property to come over to the limit, we want a little bit more than convergence, we want uniform convergence. Okay? So let's see if we can get uniform convergence for this sequence. Okay, there are two approaches to this. One is we could just define the limit I'm not sure why I'm not doing that. Well, anyway, I'm going to follow the book for a second. We could just define the limit. But I'm going to instead use the Cauchy condition for uniform convergence. Okay, we didn't quite get to it. but the Cauchy condition says what you think it should say. If you compare any two functions in the tail, and the difference between them is always small, then you have uniform convergence. Okay, it's just like it's just like the Cauchy condition for sequences. Okay, and it's well, I'll cite it when we do it. So I'm going to be comparing two functions in the tail. Now, here's a thing to remember back when we were looking at uniform convergence a couple lectures ago. Even if you look at the function like x, you're not going to get uniform convergence on the whole real line. Okay, and the point is just that the function is getting bigger and bigger and bigger. So you need to restrict it to a to some kind of bounded interval. Okay, so we're going to restrict to a bounded interval. So we're going to consider values of x in some bounded interval. We might as well make it closed and bounded. It doesn't matter. Okay, so we're just restricting our attention because we couldn't expect uniform convergence on the whole real line, but we can hope for it here. And I'm going to compare two functions from the tail. If we hadn't already figured out this proof, we would be leaving that blank right there. Okay, but we're following the book, so we've already got the proof figured out, so we already know what conditions we need. Okay, now I'm going to compare the two functions em and en. And this is for any x in that interval.
Dr. Donovan?
Yeah.
So this a is a real number, and these m and n's are natural numbers?
Oh, yeah. Yeah, if you can read that. Okay, so we go up to our definition of e's. What do we get when we subtract them? E sub m, well, m is the larger subscript. So we're going to get all the things that are in E sub m, but not in E sub n. So we're going to start at the n plus first term. And that'll go up to the nth term. That's the difference between these two functions at the point x. Okay, we want to bound this, make it small. We'll take our time here. I'm going to pull out the common powers of x. So I'll get an x to the n plus 1, but I'm actually going to pull it outside the absolute value. So I'm going to write it as absolute value x to the n plus 1. And let's pull out an n plus 1 factorial. And what do we have left? We'll get a 1 plus an x over, what's the next term?
N plus 2?
x over n plus 2. And now it gets harder. Then at the last term is an x to the what?
M minus n minus 1.
Good. And then over an m times m minus 1, dot, 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 all the way down to n plus 2. Okay. Now, let's bound this stuff. We want to make it small, so we want an upper bound. Absolute value of x is at most a. I'll put in a's for x, and now I want to make these fractions larger, so that would mean making their denominators smaller. So I'm going to replace every term in the denominator with an n. So instead of n plus 2, we'll have an n. And we will get to the end. We will have an a to the m minus n minus 1 over an n to the, how many things do we have in there? It is the same. M minus n minus 1. Okay, we're getting there. Now let's leave the outside the same. Okay. N is greater than 2a. So a over n is less than 1/2. And when we get to the end, we will have less than 1/2 to the m minus n minus 1. Okay. And now, what is the sum? What is a bound we could use on that?
2.
Mm-hmm. Good. 2. So this is less than 2. In fact, it's a strict bound, right? There we go. It's less than 2 times a to the n plus 1 over n plus 1 factorial. Okay. A is some fixed positive real number. So this goes to 0 as n goes to infinity. Is that okay? Are you willing to believe me on that limit? Have we done that limit?
I believe we have. So what you're saying so far is that basically for any epsilon, we can pick n large enough that 2a to the n plus 1 over n plus 1 factorial will be less than epsilon.
Yeah, although, yeah, the epsilon will depend on a and will depend on a.
Mm-hmm.
Okay, so
Can you say that one more time?
yeah, so I'm saying here that the limit as n goes to infinity of 2a to the n plus 1 over n plus 1 factorial equals 0. for
So
every fixed A.
I'm just a little confused how we're going between this Cauchy style thing to this thing here. So I understand that this limit is 0. That makes sense. But I'm a little confused on
Oh,
how
okay.
that says that the sequence is Cauchy.
So here's what we're really claiming. For every A and for every epsilon, there exists I think we use H usually for Cauchy, don't we? And I guess I want H to be greater than or equal to, well, how about just greater than 2A, such that for all, there's a lot of quantifiers in here. Oh, I should have said epsilon is greater than 0. We have probably want to say m greater than n right there.
Okay, I see it now.
And now I want to add a for all x in a lot of quantifiers here.
Okay. And because this limit here can be made arbitrarily small with choices of n, which means of choices of h's, then we get, okay, I get it now.
Cool. Okay. So this is the Cauchy criterion for uniform convergence. Now again, we didn't get to this. This would have been 2 lectures ago in section 8.1. We didn't get to the Cauchy criterion, but I hope you'll believe that this implies that we do have uniform convergence to some limit. Okay, and I will also, I mean, it's a good idea to go back and look at that. So let me give you the reference. It follows by the Cauchy criterion for uniform convergence, which is 8.1.10, that our sequence converges uniformly. On every one of these intervals. Again, it doesn't converge uniformly on the real line, but we couldn't have hoped for that.
Excuse me. So when we talk about uniform convergence, it has to be uniformly converging to something, because when we did it in class, we had a function already that we were saying it converged to, but now we don't even know that function exists. Yeah.
Okay, so again, well, this is what the Cauchy criterion buys us. If you think back to regular sequences, the big advantage of the Cauchy criterion then was that it guaranteed that there was a limit.
Mm-hmm.
Okay, and in the functional context, the same thing is true. If you satisfy the Cauchy criterion, there is a limit that you do converge to uniformly.
Okay, when you say there's a limit you converge uniform, that's a number, not a function.
No, it is a function. Oh, before it used to be a number. Now with these sequences of functions, your limit object is a function.
Okay.
So what I'm saying is that this guy, this Cauchy criterion, implies there is a limit function e of x.
So now that we know this exists, we just need to show that it inherits the properties.
Yeah, well, we should define the limit here.
Okay.
So for define for every real number x, we're going to define e sub x to be the limit of the e sub n's at that point. Okay, this is our usual thing, that with sequences of functions, we always define the limit object pointwise. Okay, even if we have the nicer convergence, which we do here. We have the nicer convergence on any closed, or on any bounded interval. Here, let me just go over this one more time. I want to emphasize that this definition here you can go back up here. If you consider x to be fixed, then for every x there is some a, so that we can put x in this bounded interval. These computations will all be true. So if you consider x to be fixed, what we showed above was that the sequence En of x is a Cauchy sequence of real numbers. Okay, if we think about x as being a fixed real number. And therefore, you know, based on stuff from like chapter 3, it's clear that we have these limits. Okay. It's what we're getting out of the Cauchy criterion for uniform convergence is that the e sub n's converge to e sub x on any bounded interval uniformly. Okay. Now, what were we trying to prove? There's two properties. We want, no, not those two properties. There we go. We want the derivative to be itself, and we want the function to be 1 at 0. Okay. Well, if we look at our definition of the e sub n's, these are all clearly 1 at 0. Okay, so e sub x, the limit e, the limit function e, will have to be 1 at 0 as well, because it's the limit of a bunch of functions that are 1 at 0. And then the only question is, what about the derivative? Well, that's going to carry over because of uniform convergence. So let's just write the end of the proof here. Since e sub n of 0 is 1 for all n, e of 0 is 1, proving b okay. Now, I mentioned at the end of last lecture this condition on derivatives. I mentioned the messy one, which involved the derivatives converging uniformly and us pinning down a point. And then I mentioned a weaker version, which is just if the functions converge uniformly and the derivatives converge uniformly, then the limit has a derivative. Okay, we actually satisfy that. So notice that if we look at the sequence of derivatives, Well, we proved that the derivative of e sub n plus 1 is just e sub n. So this sequence, the sequence of derivatives, also converges uniformly. On any interval. We have to be a little bit careful here. We only did it on bounded intervals because that's the only place it can be true. And then we appeal to derivatives carrying over if we have uniform convergence. That means that E is differentiable on this interval. Okay, and we know what its derivative is. Its derivative is the limit of the derivatives of the e sub n's. Well, that's the same as the limit of the derivative of the e sub n plus 1's. And those are literally the e sub n's. And we have defined that limit to be e of x. And again, this is true for all x in this bounded interval. Okay? And now we finish the proof just by doing one of our standard tricks. Since A is arbitrary, this proves the first part of the theorem.
So maybe I missed this, but why were we looking at uniform convergence only on these bounded intervals?
Because we can't get it on the whole real line.
Okay.
Is that because these e sub n's are unbounded?
Yeah, the e sub n's are unbounded. I mean, strictly speaking, it's because the differences in the tails are unbounded. So look at this. Look up here at our computation. If we didn't have a bound on x,
Okay, I see.
then that's not then we're not going to be able to do that step.
Mm-hmm.
Okay?
Okay.
So if we don't bound the interval, then this isn't going to work out. In general, I mean, it's just a general idea that you can't hope for uniform convergence on the whole real line unless you've got a really silly sequence, or
So
Yes, thank you.
maybe this is a misunderstanding on my part, but if you're working on any interval and you have a sequence of functions that's pointwise convergent, you can just take the max of all of the n's and then make that uniformly convergent on that bounded interval, right?
No, because you can't necessarily do a maximum because there's infinitely many points.
Oh, right. Okay.
Yeah, we saw an example like that where a max wouldn't work.
Yeah. Okay.
But in this case, we do it on any interval, it works out. And having uniform convergence on any interval is pretty much just as good as having it on the whole real line. Right? Because then anywhere you want to use your uniform convergence, you just say, well, okay, pick an interval that I'm within, use the theorem, and then you say, like we did at the end of this proof, since the interval was arbitrary, we're fine. Okay. Okay. So there we go. We proved that there is a function that is its own derivative and which is 1 at 0. We would like to get all the other nice properties out of this. Obviously, we don't have time. It's in the book. Let's talk about it briefly. Since you can take one derivative and you get the function itself back, obviously you can take as many derivatives as you want. Right, because the second derivative will be the derivative of the first derivative, which will be the first derivative of the function, and so on and so forth. What about some other facts that we've shown? Go back up to here. By induction, we computed this. Okay. So here's a fact. As long as x is non-negative. Oh, I see. Okay, hold on. Let me make x strictly positive. As long as x is strictly positive, e of x is greater than 1 plus x. That follows right out of that. What about, I was asked, when we stated this theorem, theorem 8.3.1, I was asked, do we want to insist that it be unique? We do. We just didn't want to throw it into that theorem. So if you look at theorem 8.3.4, this function is the unique function from, I have to specify the domain and range, well, at least the domain, so I have to specify the domain and a unique one that satisfies these two properties. Okay. Now, there's a slight problem with even if we had time to prove this, the proof relies on Taylor polynomials, which we have skipped. Okay, so if you remember enough about Taylor polynomials from Calc 2, you are encouraged to look at the proof. The idea of the proof is just if there were another, then you look at the difference between that one and this one, and you expand it as a Taylor polynomial, and you find that that Taylor polynomial is just 0. Okay, so that means they have to be the same thing. Okay, so given all this, we define E to be not E of 0. We define little e to be E of 1. And we define e to the x to be E of x. Now, if we're going to use power notation, we really ought to prove that this agrees with taking powers of this number e. Okay? That is theorem 8.3.6. So, it proves a couple properties of E. Of E. Here's one of them. I said powers, but I'm going to give this one first. E of x plus y is E of x times E of y. And property 5 is, and I'm just using the book's numbering. For all rational numbers, E of r is E of 1 to the r. Okay, and really this is two. You do this in two parts. You say for P and Q in let's just take it to be natural for now. You say E of P is E of 1 to the P, and E of Q is E of 1. Oops, sorry. E of 1 over Q is E of 1 to the 1 over Q. So to prove that, you prove it in two parts, and then you use the multiplication of powers, and you get it for all the rational exponents. Okay? Now, here's an interesting question. Do you get it for all the real exponents?
We didn't define what x meant. We didn't define it for real.
Exactly, that's exactly the right answer. We did not define exponentiation for real numbers. Indeed, this is how we do it. So if alpha is going to be our real power, and let's let x be a positive number, let me stress this again, we define x to the alpha. Oh, I see, I've jumped ahead of myself. I'm trying to finish this section really quickly. This is gonna be our last thing. Let me just put it in here. This capital function, this function e to the x, you can show it's strictly increasing. So it has an inverse. And we're going to call that inverse. We're going to call that inverse natural log. And I guess I'll copy the book. I'm shocked the book uses ln instead of log. But anyway, we'll use ln. Okay. And here's our definition of exponentiation. X to the alpha is e to the alpha ln x. Okay. And now what do you want to do? I mean, this section has a lot of stuff. Now what do you want to do? You want to verify that actually this definition satisfies all the power laws that you want. And then the function, and then the section is finally over. Okay. So the summary of today is we proved that there is a function e that looks like e to the x in terms of its derivative and its value at 0. And then we talked about other properties that you can get out of this, and I refer you to the section on that. And then we finally defined exponentiation by arbitrary real numbers in terms of e and natural log. Okay. Has anybody seen this definition before?
Yes.
Yeah, where?
Complex.
Yeah, that's exactly what I was going to say. This is how you define it in complex analysis. And in complex analysis, you're defining it for complex values of alpha. Okay.
I have a question about this definition, or kind of how it is out there.
Mm-hmm.
Does this agree with like what you might? Because at first when we discussed real exponents, it seemed like we would use some type of
Limit?
Yeah. Does this agree with the limit style definition on the real numbers?
Yep.
Okay.
But that's the thing you'd
That's
want to,
good.
you'd want to prove.
Yeah. Okay. That's good. I'd hope it did, because
Yeah.
that seems like a natural kind of definition.
Yep. Everything works the way you think it should with this definition, but it's it's a lot of work to go through and show and check that every single thing that you think should work works. Okay.
Excuse me.
Mm-hmm.
So, how do we even practically compute the values of e to the x for a real number?
Well, you ask your calculator.
Oh, well,
Or better yet, your computer. How does your computer do it?
yeah.
It uses the Taylor series.
Taylor series, got it.
Yeah. If you want to know e to the x, oops. It just goes and computes that. Before computers, I mean, this is what people had slide rules and if you go to, I don't know if it's still true, but when I first got to UF, this is, like a decade ago or something, if you went into Marston, you went to the fourth floor where the math books are, they still had books of logarithms and exponentials in there. So it's literally
Wow.
books where you just open up the book and, you find the page that has the number you want to take the exponential of, and it's there.
Interesting. Okay.
Right? That's how people did it before computers. Is they, any engineer or scientist would have to have all these books of exponentials and logarithms to look up.
Ouch. All right.
Okay. Let me, I'll stop the recording.